All right, great. Well, yeah, thanks so much for the invitation to be here and to speak here. I cut out a pretty broad swath of work in my title. I thought I'd talk a little bit about how we can use volcanic glasses and melt inclusions to understand more about magmatic processes. Obviously, this is a big task, so for the sake of time, I wanted to focus on one element that I think is going to be really exciting for this community, and that is sulfur. So this is a picture from the 1970s of Maurice Kraft, a really famous volcanologist, next to this really impressive pile of native sulfur at a fumarole. We've known for a long time that sulfur is intimately linked to volcanic activity. But I think in the context of SZ4D and the goals of this project, I'm super excited about studying sulfur in particular, because I see it as one of the best ways to link what we know about prior eruptions and what we can detect during active volcanic phenomena. So I'm showing here a really nice summary from a review paper a few years ago, demonstrating some of the ways that we can learn about sulfur in volcanic systems. And I've broken it down roughly into active and prior eruption activity. So during active eruptions, one of the reasons we're so interested in sulfur is that it's one of the easiest volatile elements to detect. So during direct sampling of high temperature volcanic gases, during ground-based monitoring efforts, and through satellite data, we're able to detect sulfur during degassing events pretty well and very well compared to most other volatile elements. And so this is particularly exciting for me as someone who works a lot with melt inclusions, because we can compare this real-time data to what we learn about melt inclusions, what we can learn about sulfur from melt inclusions. And so I'm showing an example of a melt inclusion here from this paper. You can think of melt inclusions as kind of like magmatic fossils. These are small parcels of silicate melt that get trapped within a growing crystal. When a magma body erupts, that parcel of silicate melt gets quenched into a volcanic glass. And so these are incredibly interesting and useful to study because they can retain information about volatile elements, things like sulfur, water, chlorine, that would otherwise degas during eruption. And so I just wanted to speak a little bit about advances in understanding sulfur in the melt inclusion record and how that links into other data streams. Okay, so that was my pitch for why sulfur is so interesting and exciting. If it's so important though, why don't we already understand it? Why are we still talking about it after all these years of subduction zone research? So it turns out that sulfur in comparison to other volatile elements is a little bit tricky. And these complexities have previously hindered our efforts to understand it in detail. So one aspect of sulfur behavior that makes it a little bit tricky to study is that it partitions into vapor phases and gas phases, just like other volatile elements like water and chlorine. But it additionally partitions into these sulfide phases. And so at high temperatures, these are often immiscible iron sulfide liquids. And so if we want to understand how sulfur is behaving in a volcanic systems, we really need to understand how sulfur is distributed between all of these three different phases. And so just to illustrate that, I'm showing here a really nice 3D rendering from an experimental study looking at kind of the physical interplay between all of these three phases. So that's one challenge that makes sulfur a little bit tricky to understand. The other challenge with sulfur is that its redox behavior gets a little bit complicated in subduction zones. So what I'm showing here is a plot of sulfur valence state as a function of magma oxidation state. So higher values on the x-axis means that the magma is more oxidizing. And I just want to highlight here that this calibration is showing the transition from a sulfide-dominated silicate melt where all sulfur is dissolved as S2- to a sulfate-dominated silicate melt where all sulfur is dissolved as S6+. But what's most important about this kind of calibration is that there's this transition region where sulfur is present in some proportion of both of these two chemical species. And so because these chemical species are so different, this has a huge impact on the behavior of sulfur. It makes the behavior of sulfur in ARC systems incredibly dynamic and interesting because it just so happens that ARCs straddle this transition almost completely. So in many ARC magmas, we have some mixture of sulfide and sulfate, and that directly impacts the behavior of sulfur and how it moves through all these different phases. Okay, so sulfur is complex, interesting, but I don't want to paint a grim picture here. It is definitely worth studying. And what I'm really excited about is that we have a couple of new approaches that are becoming increasingly popular that I think will help us make huge strides forwards in understanding sulfur and volcanic systems. So one method that's increasingly being used to study sulfur and volcanic systems is measuring sulfur isotopes directly within melt inclusions. So these are in situ analyses of these little magmatic fossils. And this is thanks to increases in the resolutions of techniques like SIMS that have small spatial footprints. And so the value of these kinds of analyses is that unlike kind of bulk analyses of volcanic rocks that have already degassed, we can get snapshots of what the sulfur isotope composition of the melt was while it was still at depth. And what's even more valuable about this data set is that we can compare it directly to high temperature volcanic gases that are sampled at the surface. So that helps us address kind of this distribution of sulfur between these phases. We can start to use sulfur isotopes as a tracer, but what about redox state? So there's another technique that's becoming increasingly used in the study of melt inclusions, and that is Zane's spectroscopy. So Zane stands for X-ray absorption near its structure. You can think of it kind of like a really high resolution version of XRF analyses. And because you're analyzing these small samples with really high intensity X-rays, you can actually extract information directly about the valence state of redox sensitive elements like sulfur and iron. So this is really exciting because now we can again measure the valence state of sulfur directly within these tiny magmatic fossils, these melt inclusions. And I'm just showing an example of some Zane spectra here for some reference materials. And I just want to show you what it looks like to see differences in sulfur valence state in these spectra. So we have sulfate with this really sharp peak at higher energy, and then this broader sulfide peak at lower energy. And so these are really distinctive differences in the spectra that we can actually use to calculate the relative portion of both of these two species when we measure these kind of signals in silicate melts. And I'll just highlight that these analyses usually take place in synchrotron facilities, which we have 2 of in the US that are kind of specialized in this type of analysis. And so they're really exciting work, and I think a tool that we can really take advantage of as a subduction zone community. Okay, so those are the 2 tools that I'm super excited about. I really think we'll be able to use them to make a huge amount of progress in understanding this key element. And so I just want to run through 2 different questions that we're making headway in already using this kind of approach. So the first kind of question pertains to a kind of arc scale view of subduction zone settings. And what I want to focus on here is what the source of sulfur in arc magmas is. So how much sulfur that we see in arc magmas is coming from the subducting slab? How much is it coming from the ambient mantle prior to subduction? And can we tease out the relative contributions of those different reservoirs? So to do that, one of the best things we can do is compare these sulfur isotope analyses to geochemical proxies for slab-derived material. So just to walk through these axes for the non-geochemists in the room, don't worry, I'm going to explain them. The x-axes that you see on these plots are geochemical proxies for slab-derived materials. So higher values is an indication that there's more and more slab-derived material present in the mantle source for each of these volcanoes that's plotted. I should add that these are melt inclusion suites and volcanic gas samples from different volcanoes in a given arc segment. So that's the x-axis. And then the y-axis is showing the ratio of sulfur 34 to sulfur 32. And what's really interesting about these data sets is that they all show a really consistent correlation between higher portions of sulfur 34 and increases in slab-derived material. And these kinds of observations are incredibly exciting because we're starting to be able to establish really direct links between the sulfur that we see in arc magmas and what we know about these broader subduction zone processes and the mass transfer of slab-derived material. So I'm incredibly excited about these kinds of observations coming online. We can also make similar comparisons using Zane's analyses, so direct measurements of sulfur valence state. What I'm showing here on the left is a really similar plot where we have proxy for slab-derived materials on the x-axis, but this time I've plotted the valence state of sulfur and specifically the proportion of sulfate present on the y-axis. And again, we see a correlation here, which is incredibly exciting again, because we're seeing that we can tie not just the concentration of sulfur in arc magmas to what we know about the subducting slab, but we can also start to tie the chemistry of sulfur and the redox state of sulfur to what we know about the subducting slab. And so I'm showing an example here that's kind of a regional study using melt inclusions from the Southern Cascades. But we recently published a compilation of melt inclusions from a global setting, and we're starting to see similar patterns. And so I feel really confident that this is a framework that we can use to explore a lot of different subduction zones, not just the specific ones that have been covered so far. And I just wanted to, I don't have time to walk through all of these models, of course, but I did just want to highlight what I'm so excited about these two approaches is that they allow us to directly constrain the mass transfer of sulfur and the redox exchange of sulfur with other elements at the same time. And the reason I find this so exciting is that it allows us to make quantitative models of mantle melting, the transport of sulfur that we can directly compare to melt inclusion data. And so I just wanted to show this set of models here in these different colors that it's compared to melt inclusion data. This is all published, so you're welcome to read more about it. But I just view this as one of the most exciting things we can do with these data sets is use them to really make direct quantitative estimates that we can compare to other sorts of data. Okay, so that's an overview of how we can use these kinds of techniques to look at kind of arc scale, subduction zone scale processes. We're also really concerned with what we can learn about individual volcanoes and what we can learn about kind of what we're terming the transcrustal magmatic system. And so I'm going to talk a little about some studies that have been moving forward our understanding of how sulfur evolves as it ascends through the crust. So the first study I want to show is an example of how we can use sulfur isotopes in melt inclusions to understand degassing patterns. This is an example from Hawaii, from Kilauea volcano. So keep in mind that the behavior will be slightly different in arcs, but I think it's a great example of the potential of what we can do with this kind of data. So on the right-hand portion of this plot, we're seeing a melt inclusion data set in the back. Whoops, sorry, got ahead of myself. Melt inclusion data set in the background. So each of these symbols are melt inclusions. We have the sulfur isotopes in those melt inclusions on the x-axis, and on the y-axis is the sulfur concentration of those melt inclusions. And we see that there's a correlation, which the authors interpret as a degassing pattern. And what's exciting about these observations is that we compare them directly with quantitative models of sulfur degassing that contain information about the sulfur valence state and the sulfur redox chemistry. And so getting melt inclusion suites like this that capture degassing patterns using sulfur isotope systematics as tracers of sulfur behavior, and then directly comparing them to models of degassing behavior is a really exciting step forward. I also just wanted to take a quick moment to highlight, again, how we can use this sort of information to make really direct comparisons about what we know about sulfur degassing at the subsurface to what we see in active volcanic phenomena. So I just wanted to highlight some recent work by Shuo Ding at Lamont, constructing sulfur degassing models that allow us to compare what we know about the vapor phase at depth to what we can measure, things like CO2 sulfur ratios at the surface. And so I'm really confident that as we continue to make these new measurements and how as we continue to refine our sulfur degassing models, we'll be able to make a lot of headway. I'm running short on time, so I won't spend a lot of time on this figure, but I just wanted to highlight too that all this data is at its most powerful when it's used in conjunction with other constraints from other parts of the geologic record and other remote sensing techniques. So super excited about the future of sulfur, and I hope I've convinced you to be excited too. Thank you.